Thank you, ladies and gentlemen, for joining me at Hack in the Box Abu Dhabi. I'm really glad to be back here after 2 years. I was thinking back about the last time I was at Abu Dhabi. I released ARMX, and that time ARMX was my firmware emulation framework. I made it a special point to release it at CyberWeek. We made a nice inauguration, and I put it up on GitHub. This time I'm back with a little more. I'm definitely going to talk about ARMX, and the things we can do with ARMX is a nice little practical demo about firmware emulation and extraction, which we will do. But I also wanted to introduce a massive and a major update to ARMX, which is called Emux. So folks, Emux is the new ARMX. Why did I do that? Because now ARMX no longer just emulates ARM IoT devices. ARMX, along with ARM, I added MIPS support. So I can't call it ARMX. I can't call it MIPSX. Well, Zoltan's calling his framework as MIPSX. So we decided to call it Emux, because now it's a more generic framework for emulating several things. It's also available as a Docker container. I will talk a little bit about Emux in a bit. For an introduction, my name is Saumil Shah. I've been, as I say, educating, entertaining, and exasperating audiences since 1999. I've been around for a long time. This was actually a picture at one of the Hack in the Boxes at Kuala Lumpur. So, talked about ARMX, which is now Emux. All the documentation has been updated. You could find it on emux.exploitlab.net. The Git repo has been updated. The Docker image has been updated. And you now, as a bonus, get full MIPS capabilities. What we're going to do in this exercise in this workshop is we'll take an IP camera, the TriVision NC218. We will extract the firmware from the IP camera. We're going to use hardware to extract the firmware. I will show you the kind of hardware support I've got in a little bit. Once we've extracted the firmware, we will then proceed to emulate it in Emux and get a working emulated version of the IP camera going. This lab is originally intended to be a hands-on lab. I thought about it. I do not think the current layout and the social distancing and the arrangements support so much of hands-on interaction. However, if you wish to play with these things, just let me know. We'll figure out how we can play with it. I'll give you some hints. There's some documentation. You can probably just grab the Docker image yourself and do it. And I'll share some images with you later on in the Git repository for you to try and play. Now, just a little bit of introduction to IoT devices, right? What are IoT devices? How do they work? And what are some of the fundamental differences in IoT devices from desktop computers? And we will explore these differences from the point of view of emulating them. If we want to emulate a desktop, it's really easy, right? All you do is just spin up VMware, VirtualBox, pop in an image, and boom, off it goes. But you can't just like say, I'm going to take firmware, drop it into QEMU, and it does its thing. It's not that easy. There is a plethora of complexities in QEMU and the way IoT devices are. And we really have to go deep down into understanding the architecture of IoT devices and how they boot up to get an idea of how these can be emulated. So a couple of things. I'm just going to first talk about the architecture of IoT devices for a few minutes. We'll talk about the boot up sequence of IoT devices. Then we'll proceed to do the firmware emulation, the firmware extraction using hardware. Here's the hardware. I'll give you a closer look using the laptop camera in just a little bit so you can see what's going on. And once we get the firmware, the next phase will be breaking that firmware up and emulating it in Emacs. At the end of this workshop demo session, we should be able to get our hands on a fully emulated copy of the TriVision IP camera, which works just as well enough as the real thing. I use this in my training for fuzzing, debugging, and doing exploit development. You know, it is much better to do exploit development and testing on a virtual image than on a real image. You have the ability to, put tools in, pull tools out, snapshot it, reset it. It's pretty hard to do all that stuff on this little device. So that's a little preview of what's coming up next. So quick intro to the IoT boot up process. There's no spinning disk on an IoT device. There's no block storage. There's no SSD. What you have is the CPU, the system on chip, and NAND flash or NOR flash as your memory. So essentially it's CPU, the RAM that is built into the CPU in the SoC, and external NAND flash, which is implemented as serial SPI flash. And then you have your usual peripherals, which is like LAN interface, WAN, Wi-Fi. In the case of the IP camera, you have the frame buffer and the works. When you power on an IoT device, the CPU kicks in. It fetches, it's programmed to look for the bootloader at a particular location in the flash memory. All this purple stuff happens in flash memory. Now the bootloader will in turn find the kernel. The kernel will search for the flash partitions and find the file system. After the kernel finds the file system, everything happens in RAM disk. So flash, you and I are used to flash being read-writable, but truth is flash is not writable. Flash is readable and erasable. So if you think of flash memory, flash has multiple blocks. You have more blocks available on the flash chip than you actually need. So if you take like a 64 megabyte flash chip, chances are you'll have like double the number of blocks on it. The more you write to it, the old blocks will just get killed and new blocks will get consumed. A time will come when you cannot write to the flash memory anymore. It is completely borked. At that time, it becomes a CD-ROM. So all the stuff over here, right, the kernel, the bootloader, compressed file system, everything is pretty much read-only for us. When the kernel finds the file system, it will uncompress it in RAM. So you get a RAM disk, which is like your ext2 or ext3. It has, the RAM disk will have blocks and inodes and directory trees and whatnot. And then the kernel will pass the control to the user land. So init will call the init scripts. Init scripts will then read the configuration. The configuration is also in an interesting way. The configuration is not saved as files because guess what? If you have to write files, you have to update the file system. The file system cannot be updated because it is compressed and it's on flash memory. So the way changes are persisted, configuration changes are persisted, is they're persisted in a special area called NVRAM. Now, the NVRAM is erasable and flashable a bit better than regular flash memory. So the init scripts are then programmed to pull off all the configuration parameters from NVRAM. That's when you like boot a Wi-Fi router. It takes a long time to boot because it keeps on blinking. what's happening is all the config parameters are being read from NVRAM, and they are being created as config files in the RAM disk on the fly. So all your networking config, all your Wi-Fi config, all your HTTP config, your passwords, whatever it is that you're doing, default URLs, they're all built up on the fly by reading details from NVRAM. Once these config files are built up, then the init scripts will kick off services, which will be typically user-land services. And the user-land services will do your usual system things, so network, DHCP, DNS, USB, Samba file sharing, cups printing, whatever it's programmed with. And then you have the custom applications on top of the user script. So this is how basically an IoT device boots up. What does this mean for us? If we want to emulate it, we have to faithfully recreate all these steps using QEMU. Now you can do it once. What happens when you move to a different IoT device? Like, you'll have to do the whole song and dance and magic chanting once again. So it gets to be a little painful, and that's why I, as a researcher, started creating shell scripts to automate this process. And then the shell scripts need more shell scripts to automate the shell scripts, and so on and so forth. And you need debugging tools, and you throw that in. You then end up saying, I don't want to use a default kernel, I'm going to recompile my own kernel. So you create kernel compilation scripts, and pretty soon a framework is born. And that was the genesis of ARMX, and now Emacs. So yeah, once you have the applications ready, the device is good to go. It's usable. We're going to now focus on two phases. We're going to focus on extracting the firmware. And then the second phase is we're going to focus on emulating the firmware. There are three ways to extract firmware. One is by a simple mechanism from a bin file or an FTP server or a website or a CD-ROM. Just like download the firmware and apply it. This is cool. I mean, you can get the firmware, but you will not get the running configuration values. It will be like empty blank in default initialization. The second and most popular way is to find basically the serial console. So you open up the IoT device, you find the UART, voltage, ground, transmit, receive. There's like hundreds of YouTube videos showing you how to do that. Connect it to a serial port, get a shell, and then extract all the partitions using DD out of the shell. We're not going to do that either. What we're going to do is we're going to do step number 3, that is extract it directly from the flash memory. I feel that is the, what shall we say, the most close to reality image that you'll get from the chip. Like literally just pulling the bytes of the chip itself. It's the purest image, and then we'll work on figuring out how to emulate it. So yeah, website, this is the serial console. You can see over here that I've found the serial port on the IP camera, connected these leads. They all go to the serial adapter on my PC. You get a serial console over here, and then you can get a shell and you can do the DDs and whatnot. This is how you take it directly from the chip. I have a flash programmer. This one's called the A6 Forte. It has a chip clip. So you can literally take the clip and put it on top of the flash, and then the software will suck everything off it. I mean, it sounds simple, but in reality, it's not that simple. There are some reasons why you may not entirely succeed with this technique. I mean, this technique was successful. I was not able to bring the whole IP camera over here, and I didn't bring this one. Instead, I brought something different. So I'm going to show you what we're going to use for firmware extraction. First, a little bit introduction into serial flash memory. Let me also open up one minute. I'll use the poor man's video camera called FaceTime. There. So let me show you what the flash memory looks like. A bunch of flash memory chips in here. So what I did is I actually used the soldering gun, hot air gun, sorry, lifted the flash chip off the IP camera, extracted the firmware, and then for test purposes, I cloned the firmware into different flash chips. So this is one example of a flash chip. You can see over here. This is a SPI flash chip. It is an 8-pin package. It is also mounted on a breakout board, and all these header pins make it easy to connect to any extracting device. Otherwise, you have to like have a clip which goes on top of the legs. It gets a little messy. So for lab purposes, it makes it easier. I have like several clones of firmware in here. Like this is all the IoT devices, various chips, all cloned. And one of them is plugged in over here. I believe I stupidly dropped one of them. So we'll find it in a bit. There's no hurry. Not a problem at all. We can take our time doing this. Yes. What am I going to use for the firmware extraction? Let me show you. So I don't have the A6 Forte, but I have a very, very fantastic tool. And this is developed by a good friend and a luminary in hardware hacking, Joe Fitzpatrick. So this is a board called the Tigard. The Tigard is like a Swiss Army knife for anything JTAG, anything SPI flash, anything I2C, anything serial port. He's got the various interfaces over here with different header pins. They're beautifully labeled. It also comes with a nice table of connections. Like you can create it has got the cheat sheet behind it. He's thought of everything, like how you design a circuit board for testing. He's got the best leads available. And you can see this Tigard is plugged into my IP cam breakout board flash chip. I will show you how the wiring is done in just a little bit. So we're going to use this, and we're going to then extract the firmware using a very easily publicly available program called FlashROM. FlashROM is pretty standard. It comes with mostly every Linux distribution, or you can like download it, configure, make, install it. It's easy. It's easy to get. And not just the Tigard, but there's a lot of devices that lot of hardware devices that support FlashROM. So FlashROM is able to read from several things, even a Raspberry Pi. Although I highly recommend the Tigard for two reasons. Number one, it's a very, very efficient device. If you want to do this often enough, invest some money. It's not very costly. It's like $80 or something. Invest the money into getting a good device. You will not go wrong with it. And second, it's open source hardware. It's developed by a friend in the cybersecurity community, and you should just like support such projects. It's really cool to do so. Help the underdog, right? So with that being said and done, let me give you a walk through flash memory. This one's an 8-pin package. You have chip select as pin 1. Now, chip select is a weird pin, right? If chip select is pulled low, that means that whoever the CPU has full control of the flash chip, and it will not. It's not available for any other use but for the CPU's own use. Now, several times I've noticed when I try to extract flash from the hardware, like say IP camera has a flash chip on it, then you connect all the pins and you try to extract the firmware, you have to supply the voltage to it. When you supply the voltage to the flash, the voltage track also leads to the CPU. The CPU gets activated and then it holds the flash chip and doesn't let you read it. So one way is you have to like either short the CPU by finding out the voltage to the ground and not let the CPU get activated, or the easiest way is to literally just melt the solder, lift it, read it, and then melt it again and place it back. Easier said than done. I have bricked 3 routers by trying to place it back. I've burned the board, I've burned the chip. So there are people who know how to do it really smoothly. They've got steady fingers, calm hands, and very precise touch. I have none of these 3 qualities. So I screw it up. And that's why I create clones. Once you get it off, create a clone, and then we'll make it easy to read. Okay. Now serial flash is pretty much like there's only 2 IOs to the serial flash memory. There's data out, pin number 2, labeled DO. Pin number 5 is data in, DI. And then there is a clock. So the clock keeps on giving the signal. Data out and data in is where you read and write the memory. Now there's an SPI protocol that is implemented in flash ROM and on these boards and everything, and these chips follow it too. And this is how we have made the connections with the Tigard and the SPI flash. So one of the breakout pins on the Tigard is literally 1:1 mapping with the SPI flash. I mean, Joe Fitz has so beautifully created the pins exactly in such a way that they just literally map directly to the 8-pin layout. You don't have to figure out which wire goes where. Even if you do, there's a cheat sheet on the back. So I have wired 6 pins on the Tigard to 6 pins on the breakout flash chip. The only 2 pins that I have not wired are the chip select and the chip select is wired. The WP, I forgot what it is. Something protect. It's not write protect, but something protect. It'll come to me if it does. And the hold pin. These are the 2 pins that are not connected. The other 6 are. And now, so this is what I did in a nutshell. This is the SPI flash on the IP camera. I lifted it off the IP camera. I cloned the contents into this chip. Basically, it's the same. That one's a WinBond. This one's a WinBond. I tried to match the chips the same. Created a copy, and now we'll work off this copy. So, a little bit of demo time now. Okay. This is readable now. Excellent. Yeah. So you're going to use first. Let me check if the Tigard is detected. So when you check the D message, you plugged it in. I plugged it in just before I began the talk. So yeah, the Tigard is detected. It shows you that it has these FTDI USB, TTY USB 0 and TTY USB 1 interfaces ready to go. So now we can use flash ROM to pull the image. I mean, it's all going to sound dramatic, but it's not going to look dramatic at all. Let's make a directory, HITB. Nothing in here. Now, we'll supply the flash ROM command. And what you see over here is the flash ROM command will accept the port that you're reading from. That is the FT2232 SPI interface. And then you have to choose which port. Now this divisor is an interesting value. It tells flash ROM by what factor to divide the clock speed. And sometimes slower is better because it will get you a more accurate read. Now, with trial and error, I found that 4 and 8 work quite well. And then I'm going to read everything in this file called ipcam_flash.bin. So it said, yeah, it's found the wind-bound flash chip W25Q64. So W25 is like wind-bound's SPI flash package type 25, which is 8 pins. Q64 means it is a 64 megabit, which is an 8 megabyte flash chip, and it successfully read the memory. Now, if you do a file list, it's exactly read 8 megabytes of flash memory in this file. I've memorized these MD5 sums by heart, so if it starts with like 686 something, it's correct. Let's just make sure it read it accurately. Well, no, it didn't. Okay. I fortunately have a backup copy. See, I'm going to try and read it again because this was what it's supposed to be. And this is, so 688 is what we need. I'm going to try and read it again. Now we got it right. So it happens, you know, you must test. Sometimes if you're doing the firmware extraction for the first time, you want to do it 3 times with different divisors and then pick the best 2 out of 3. If you get all 3 of them very different, slow down, you know, increase the divisor to a greater number. So you slow down the clock. You do this until you get accurate reads. Otherwise, you don't know, you don't have a source of truth. So yeah, this is what will happen in production. This can bite you. All right, now we have a clean copy. We're going to take this clean copy and we are going to now do firmware extraction with it. Okay. So we will now switch over to Emacs. And Emacs is pretty awesome. This whole thing is available as a Docker image. What I'm going to do first is I'll just perform the extraction. Once we have a clean, I've performed the extraction, I'm sorry. I'll import it into Emacs and we will analyze the firmware and we'll divide it into the original flash partitions that it is put, that were put onto the chip. Once we do that, I'll give you a tour of Emacs and then we'll figure out how to emulate it and move forward with it. All this is available on the Emacs website in part of documentation. So the steps on emulating, case studies on emulating devices, it's all published. I'm just going to repeat those same things over here. Let me go to the workspace. I have the old IPCam flash. I'm going to remove it. And let me SCP this from the machine that I extracted it from. I've been doing workshops and presentations for 20 years now. There's a train of thought is like you should have backup videos of everything, because if the demo fails, then you just play the video. I'm one of those stubborn idiots who will insist on doing it live, and if things fail, fix it on stage. Because if it can't work on stage, it can never work at all. So we're going to do this once again. I never have backup videos for 2 reasons, because I'm always testing new changes till the last minute, and then I'm too lazy and too sleepy to make a backup video. So we're going to do this for the very first time. I had stored it in the HW directory, HITB star.bin. There we are, the flash memory is copied in this workspace directory. We now have the workspace to play with. Now this workspace directory is interesting because it is going to get mounted into the Docker image. It gets mapped into the Docker image, and everything we'll do now, we will do in the Docker image alone. One moment. Running Emacs is as simple as building the Docker image and then invoking run Emacs Docker. So it does some port forwarding, and then when you see this Emacs prompt, you get to see you're at the Emacs prompt. You're ready to, you can type in launcher, and it will give you a menu of all the emulated devices that already exist. I've got 13 devices emulated so far, the latest ones being these two damn vulnerable MIPS routers. There's a little endian and a big endian. A very interesting CTF challenge with MIPS is going to be published on the 4th of December, along with the phone CTF that Excel April is running in France. So I've built a MIPS CTF for her, which will also get released into Emacs on the 4th of December. It's a very, very interesting exercise on memory corruption. If you wish to play with MIPS, I suggest you get your hands dirty and your feet wet with that CTF. Look for it on this one. Okay, but we're not going to do the launcher now because we're interested in creating our own device and then adding it to this menu list, and that's what we'll walk you through. So we're going to go first to the workspace. And here we have that ipcam flash.bin. We extracted this file from Tigert. We dropped it in here. Now, the easiest thing to do is binwalk it. Binwalk will usually give you a very quick overview of where the boundaries lie. So it will separate this 8 megabytes of flash into the bootloader, into the kernel, into the root file system, and any other partitions that may exist on here. Yeah, so then we become root. I'm going to go to the temp directory. First, we will do binwalk and simply analyze the file without extracting it. So I run binwalk. Folks, is this readable at the back? If you're viewing, just give me a thumbs up. Oh, it's good. Brilliant. So here we are, binwalk saying that you have a Linux kernel, Linux ARM kernel in there. You have some gzip data. This is your root file system. It's cramfs. And then there's a POSIX star archive. So we'll separate all these things, and then we'll use binwalk to separate all these things. So we're now going to run binwalk again. We have to give some more commands like run as equals root -1, which means don't clobber symlinks, and perform a binary recursive extraction on home R0 workspace ipcam flash 8m.bin. No errors. It showed you the same thing, so this means it's good. And if everything goes well, we should see exactly this file, this underscore ipcam flash 8m.bin.extracted in here. And within this file, you should see several components. So what binwalk does is it first processes this list, right? It just separates these blocks. So it separates the kernel, separates the gzip data, separates the CRAMFS and the TAR archive. And the file names it gives are based on the offsets from the beginning in hexadecimal. So if you see this file like 17324c.cramfs, it refers to this block over here. And using magic numbers and headers, Binwalk is able to identify what type of block it is. So it then tags it automatically as, oh, this is CRAMFS, this is SquashFS, this is a kernel, this is something else. If it can identify, it will. For example, in the kernel, it could not, so it just left it without an extension. And then it has a TAR archive. The 7F0008 is a TAR archive. And the TAR archive also got extracted with these files, sys.conf and umconfig.conf. The CRAMFS in turn got extracted as CRAMFS root. Now, if we navigate into CRAMFS root, here is the entire root file system of the IP camera. So now, more or less, phase one is done. We got the root file system from the IP camera, separated into individual folders and directories and files. Think of this like the mounted RAM disk. It is the uncompressed file system as if it is present in the RAM disk. Now we're going to take QEMU, boot a kernel that matches the kernel that is present on the IP camera. We'll find out what kernel it is. Unfortunately, we will not be able to use the same kernel because the hardware of the IP camera is different than the emulated hardware that QEMU provides. Now, you can boot off it, but there'll be no display, nothing, and sometimes it might just hang if it does not find the right peripheral. So what we do in in Emacs is we recompile a kernel that matches this kernel. Now, some of the drivers may or may not load, so there's a little bit of limitation over there. It does not do 100% emulation, but we try to get as close to it as possible. Okay. So rootfs done. Let's first of all fingerprint the kernel, shall we? What we'll do is we'll just this seems to be the kernel block. Let's run a strings on it. Yep, this looks like the kernel. You can actually see that this is the kernel console boot up line. And here it is. This is Linux kernel version 2.6.28, which was compiled in 2016. Okay. This is an anachronism. 2016, we already had new kernels. Why do we still use ancient kernel 2.6.28? Kernel 2.6, as it turns out, is the IE6 of IoT devices. It will never go away. And the reason is the chipset manufacturers choose to provide drivers in binary form. And the binary drivers are compiled for kernel 2.6 because somebody just got the old Broadcom toolchain, compiled it, done. These drivers will not work with new kernels because the symbols will mismatch. Nobody from the vendor side will bother to update it because there's no money in it for them to update it. Like, what the hell is the new kernel going to do? Give you a sharper IP cam image? Nope. If it works, it works. We'll ship it. There's no impetus in IoT in IoT devices to go to the latest and greatest. There's no concept of latest updates in IoT land. And that's why we have these old kernels floating around. You'll see this behavior more often than not, actually. So what we're going to do is we're going to compile our own version of kernel 2.6.28 with the ARM v5 instruction set. And then we will use that to emulate it inside QEMU. Okay. For those of you who compile Linux kernels, it is a very time-consuming process. But I mean, essentially, it's nothing but just going through the make menu config, selecting the options, and then using a cross-compiler to generate a cross-compiled ARM kernel. Fortunately, we're going to use one that we have. Along with Emacs, I also supply several template kernels. So in the Emacs template directory, you'll find kernel. And I've got a few kernels compiled. There's the ZImage 2628, which is matching the IP camera. There's 2629, 2631, 39, 316, 57. And these are the new MIPS kernels that we are also now using. So basically, once you compile a kernel, you can throw it into the kernel directory in Emacs and then use it for any of the emulation. Yeah. Let's talk a little bit about the emulation now. You know, I'm finding it a little weird to present back on stage again. For about 2 years, I was presenting on Zoom. And my desktop is laid out in, you know, Zoom region this, Zoom region that, and then you screen share this, you screen share that. And I'm like, wow, we're getting used to stage and monitors again. Like I have to keep turning this way and that way. But you know what? This is fun. This is the way to do it. Zoom's nice. This is nicer. Okay, so when it comes to emulating the IP camera, instead of the CPU, we've got QEMU. We're going to use emulated NVRAM. The kernel will compile and use our own kernel. And the file system, instead of using the compressed file system, will straight away use the uncompressed file system, which we got from binwalk. Now, to compile kernels, the best thing to use is buildroot. Buildroot has a beautiful set of cross-compiling tools. Buildroot is a little difficult to understand at first. It takes some time. But the folks who have created Buildroot, Bootlin, they have published everything for free. Tutorials, trainings, PDFs, videos. They're a generous bunch of people. I've actually personally taken a class from Michael Opdenacker, and he's been a most wonderful guy. He like shows you the insides of Buildroot and booting up and creating your own IoT device. It's wonderful training that he does, and it's all online. So all we essentially need is the kernel and the uncompressed file system. We drop this into Emacs, and then everything else will happen. We also may need to fix some config files to match the QEMU environment, stuff like IP address, because we pulled this off a running IP camera. It'll have its own IP addresses, and Emacs needs its different IP addresses to make things work. Okay. So what we have in that firmware image is this. We have the kernel, which we got. We're going to compile a matching kernel. We already have it in the templates. We have the CramFS compressed file system, which we extracted using binwalk and CramFS-CK. And we have the tar archive, which actually has these config files, sys.conf and umconfig.txt. This is basically the layout of the 8 megabytes of flash that we extracted. Now comes the whole process of how to emulate this extracted firmware. So I'm not going to bore you with the details of how the Emacs Docker container is organized. I did a talk on inside ARMX and inside Emacs a little while ago. It's available on YouTube, and the slides are also available on the website. Highly encourage you to follow that talk to get an idea of what lies inside. At a very high level, you have QEMU, you have an NFS file system which gets shared from the host within QEMU. You have a Docker volume which hosts the NFS file system. You have a workspace directory which gets bind mounted between the host and the Docker container. And you have port forwarding to forward from the host to ports inside QEMU. This diagram gives you a little bit of a directory layout of how Emacs is organized, where all the scripts are. So you have a devices database, you have QEMU options, you have all the QEMU scripts and binaries inside the run directory, you have a debug log directory, you have a host FS directory, which is like the initial file system to boot with. And then you have all these boxes in blue that you're seeing, the myIPCam and DVARM, DVMIPS. These are all emulated devices. And then there's a template which contains, well, basically a template for emulating your new device. So we're going to create a copy of the template. We're going to fill in the configuration. We're going to drop essentially we're going to drop the kernel in. We're going to drop the compressed root FS in, and we'll boot it. The documentation also discusses 7 easy steps to emulate your own device. So one is make a new device from the template. Then you compile a kernel, prepare the compressed root FS, create NVRAM if needed. If there are any flash partitions to be emulated, drop the flash binary. Any library hooks to be thrown in, edit the library hooks. And finally, you create a config file and you add an entry into the device's database. So yeah, from now on, it's all demos. Give me just a moment. We'll come back to the slides in a little bit. Just going to take a pause for a moment, breathe a little bit, have some water. We'll continue in exactly 1 minute. Yeah, I don't know where it is. It's not fallen down, right? Yeah. I found it. Got it. All good. Just one moment. Meanwhile, if you're also interested in more IoT devices stuff, right? My friend and fellow countryman Asim is presenting over there. It's kind of unfortunate that our talks had to be in parallel, because I would have really liked to see his stuff, and I'm sure you would have liked to see mine. But definitely catch the recording of his hardware stuff that is built, Exploit. It's pretty good. I mean, I would someday love to get a good first-hand demo of it, but I've heard nothing but good things about his work. Second. Okay. Right. So I'm going to now we'll now start on the process of emulation. So first, we'll make a new directory. We'll copy the template into directory called myIPCam. I'm going to go to myIPCam, and in here, all I need to do is edit the config file. The kernel is already placed in there, and populate the root file system. Now the root file system we already extracted, so all I have to do is move it from the temp directory, extracted cramfs root, and the root file system is already over here in cramfs root. We don't need MTD parts, we don't need NVRAM, so I'm just going to remove those. And we also don't need the preload directory in this case. So it's simple enough: configuration, cramfs root, and the kernel. We will edit the config file, and here I have to give the device ID. There's no NVRAM, so I'm going to remove that, comment that line out. The root FS is called cramfs root. I'm going to leave ASLR off for now. And in the init commands, I'm simply just going to do bin sh. First, we'll see if this works or not. Now, let's create a corresponding entry of myIPCam in the overall devices database. Before I do that, I'm just going to chown I'm going to set the permissions to the R0 user, so there's no problem in there. And we go to devices extra. So here, this is a list of all the devices that are emulated. I'm going to actually have this thing pretty much set. I'm going to add this line over here, and I'll explain you what it is. So here's the line that I've added. It is the device ID is myIPCam. Then which QEMU binary you want to use. So I've already got compiled binaries for QEMU 6.0 and 6.1. We can use either. Let's use QEMU ARM 6.1. If you're doing a MIPS version, you can use a QEMU system ARM MIPS or MIPSEL if it is a little endian MIPS. MIPS typically have two flavors, big endian and little endian. ARM also has big endian and little endian, but I've not really seen a big endian ARM device in years to come. Then this is the board that you'll use for ARM v5. There are different boards for ARM v6 and ARM v7. The kernel, the ZImage 2.6.28. And then this is the device name, ring 2021 IPCam. We're going to call it HITB 2021 IPCam. Welcome, Cristofaro. The device database is saved. And let's see if this this damn thing works, right? Like I said, it's all done live. There's no pre-recorded demo. If it works, it works. If it doesn't, it won't. Okay. Now, Let's do a launcher. So sure enough, you get a new entry added at the bottom. It says HITB 2 2021 IP cam. Let's launch it. The kernel does kick off, and you do have a booted version of just the kernel. This is not the IP cam working, mind you. This is just the kernel that is booted up. And what we will now do is boot up the user space component of the IP camera. Right now, there's no user space component. But we'll plug the user space component in just a little bit. So once the kernel is booted up, we pretty much don't need that panel at all. We will now attach to, we'll get a Docker shell and then use the command user space. All these are Emacs commands which are documented in the Emacs documentation. Now here, you get three options. You can either drop into the hostfs, which is the minimal file system, or we're going to start the HITB 2021 IP cam. We are not starting any system services, so we'll just get bin sh. This is the BusyBox shell of the root file system of the IP camera. If I do a file listing in here, I'm going to see only the necessary files that are present in the root file system. I'm not going to see anything else. This is basically all the stuff that we extracted, and it's now living in here. How do we go ahead from this point onwards, right? We want to now kick off all the services. So what we do is we need to find out what the init scripts do. The best way to do is to look into etc init tab. So etc init tab, you can see that the initialization is done by etc init.d rc.sysinit, and then there's etc init.d rc3. Now there are a few fixes that I'll need to do. Basically, this is the first time you start it, things will start going wrong because it's not finding the video devices, and then you have to fake the video device, or you can simply delete this video device file. How do I know all this? Because of just weeks of trial and error. When you do this for the very first time, you should be prepared to invest about a week in figuring out the boot up sequence and what devices are used. You might have to do some S-trace stuff to see what block devices or special devices are being opened. Once you do all that stuff, you'll come to know what goes on behind the scenes, and then you basically have to fake it till you make it, until you get something like this going on. So I'm going to try this first, and then we'll just skip to the final step, because otherwise we don't have a week to spend over here as much as I would have loved to do it with you. So first, let's just try etc init.d rc sysinit. It'll load things, and then you'll get an error. You'll get an error like lib modules abs628.ko, it did not load, and it kind of failed. So what I do is I go to the dev directory, remove the abs628 file. I create a blank file, abs628, which is a fake video device. And now I'll run the etc sysinit. See, now it went a little further than this. It tried to it basically did not stop over here, it went further. Now we will try etc init.d rc space 3. This was the second item. This was the second item in the etc init tab. So we'll invoke this by hand. Now what's going to happen is it'll start loading up all these essentially it starts loading up all these services. It's starting the task manager and it started the web server. It's trying to essentially bring DHCP up. But there's a mechanism in Emacs to force the Ethernet interface to 192.168.100.2, which is the default interface. Yeah. So right now it seems everything is running. If I check the processes PS, the web server is running. Now for the final test, right? Let's see if the IP camera's interface goes on. I'm going to browse to localhost 20080, which essentially happens to be port forwarding to the Docker image on port 80. And you have a virtual IP camera booted up, even though there is no IP camera over here. You can enter it. There's no video stream because, well, there is no video device. But if you look at like the settings, you can play around with the network. Go to TCP/IP settings. So at this point, this device is ready to go. You can communicate to it using TCP/IP. You can now attach GDB to it. You can debug it. You can fuzz it. You can now run exploits on it. All that stuff. And I'll show off a little bit of Emacs and the Emacs capabilities, and then we'll wrap up our session. When you get this thing booted up for the very first time, right? When the thing finally works, it's a moment of joy. Like you feel super happy. Like shit, it really worked. Because 5 days before this, you'll be banging your head against the wall. Like it goes so far, then it fails. Then it'll go further and it'll fail. Every night you sleep and you wake up, you'll then think of doing something different. It'll go further. Every shower you take, you'll get a different idea. It'll go further. Until one point, the damn thing will just work. And at that point, you just go out and say, I am the master of the universe, just like He-Man. Then you put the sword back and go start breaking these things. Now, all this stuff I basically did by hand, right? I invoked the commands by hand because I know how to make it work. What you then do is you automate the whole thing. Like you can create the init commands, what I did by hand. You can put in the config file, so automatically it boots up. I'll show you the automated version that is present in just a second. So you're going to put this away for now. And I'm going to attach another Emacs Docker shell. I mean, even from the Emacs Docker shell, it's like you could do a lot of stuff. You can do Emacs PS, which will remotely dump the processes that are running there. You can do like Emacs, if you want to get the process memory maps of the web server, you can do like Emacs maps, webs. It'll give you the process memory maps of the pages of the virtual memory of the process. So there's several little wrapper scripts that I've written to make testing, debugging, tracing, all that fairly easy. What I'm going to do now is I'm going to Emacs halt this. So Emacs halt is like the shutdown. It'll bring the system down. It will shut the kernel, and I'll show you what we do to automate this whole boot up process. Okay. Okay. So in here is actual implementation of the IP camera. If you pull down the default Docker image of Emacs, the IP camera firmware is also distributed as part of the default distribution. So you'll be able to play with it by yourself. And all the config is stored in this directory called try227wf. Let's look in that same directory. It's the same as the myIPCam, except all that automation stuff is in there. Then we cat the config file. So here is the automated init command. So first you remove the dev abs628, you touch a new dev abs628, then init rc.sysinit, init rc.3 bin sh. And with this, it would be good to go. If I do a launcher, okay. So let me first launch this. Try Vision IP camera. And we're going to go Emacs Docker shell, user space, and start the IP camera. Now all those automated init commands will kick in, and it will kick off all the processes. And now we're even ready to go. I do a couple of cool little demos. So folks, basically this is my production testing machine, right? This is what I do IoT R&D with. So anything new I need, I build it into Emacs, and then I publish the changes on GitHub. I publish these rather frequently. Okay. Let's, we'll do a little exploit as well. I'll show a nice little Stack Overflow on here, which is quite fun. First, let's make sure that the web server interface is working. Yeah. It is a web server interface. Enter settings. So yeah, this is all good to go. Yeah, all this stuff is working. So now we're ready to exploit it. I'm going to do an ARMX, Emacs GDB. So Emacs GDB is a nice little wrapper. It attaches a remote GDB server to any process that's running. We just call it, we just name the process. We know the process is called webs for the web server. We attach the GDB. So it'll spin up a remote GDB server, attach it, and then invoke GDB multi-arc to basically get control of GDB on our side. We can now run even GEF commands like vmmap. It shows you the virtual memory. So this is the process that's running, user bin webs. And let me run the exploit. So exploit is basically a very long URL with number of A's. I'm going to pipe it to netcat localhost. Oh, I need to continue this guy. To the forwarded port 80, I pipe it, and the moment you do it, you get a segmentation fault in here. You get control of the program counter as 41, 41, 41, 40. The stack memory is corrupted. So from this point onwards, you can now go and build your exploit. You can like launch webs again. So this becomes your testing grounds for creating the exploit. The beauty is the memory layout, the kernel, all the settings are exactly the same as the real IP camera. So if you got an exploit working on Emux emulated IP camera, it will work as is without modifying a single offset or a single size parameter. It will work as is on a production IP camera. And I've tested it with 3 of these IP cameras, and it works super, super reliably. So that was, well, I think I succeeded in my demo. I'm pretty glad I did, because I confess I was a shade nervous. If it blew up on the stage, then it would look like a fool, but it didn't. So the demo gods took care of me. So let me wrap this up. All the goods that you want are available on my GitHub repo. My GitHub user is the real Saumil. My Twitter handle is the real Saumil. My Facebook handle is the real Saumil. My LinkedIn handle is not the real Saumil. It is Saumil Shah. But you can grab this from my GitHub repo. Follow my Twitter ID for announcements. I don't do political posts. I don't do anything but cybersecurity. I don't engage in debates. Basically, my Twitter account is used simply for announcements. So low frequency, low noise. If you want to catch the latest, follow me. And I thank you for your time and your attention and your patience. I'm at your disposal for any questions that you may have. And I don't know how the Q&A works, but I'll let my dear friend Jaco moderate this.
Yes, I already looked it up in the app. There's no open questions right now.
Okay.
In the app, so I'm going to see if there are any questions in the room. Yep. You have to speak up really loud because he doesn't have the earpiece. Can you speak so loud that he can hear it?
Here?
No, he doesn't.
Okay. So I didn't check the repo yet.
I'm so sorry. If you don't mind just coming up here and asking, that'll be awesome, right?
I didn't check the repo yet, but I saw that you have quite some routers already configured with Emux, like the Nighthawk or the Archer C9, I guess. Are they already on the repo available for?
Good question. So not all the devices are available in the repo. Only a few of them are. Some of them I use for the training. Some of them it gets into a gray area where these vendors will create problems for me if I release it.
Yeah.
But there's nothing stopping you from getting your own firmware image and putting it on there, if you see what I mean.
Yeah.
So,
okay, perfect. Thank you.
You're welcome. It's kind of odd because I'm seeing myself talk to Barry on that big screen over there. Like, sorry, I got distracted for a moment. Like, what the hell is going on?
Any more questions from the room?
How can I be in 2 places at the same time?
So, Saumil, I want to thank you for your brilliant talk.